Now, if you want to define hazard, I have already mentioned many times, a hazard is a potentially damaging physical event of any human activity that may cause the loss of life, injury, property damage, social and economic disruption, or environmental catastrophe. Okay, so now you can see the difference between hazard and disaster. Disaster is two different definitions. Okay, disaster is what? When the community cannot be able to cope with it. That is where it becomes the disaster. So, if you want to break it down, the upper part of the definition, so that means this event has a probability of occurrence. Probability of occurrence is between 0 and 1 within a specified period of time. Time is also very important. Within a given location, at a particular location, okay, and has a given intensity. Okay, so there are four aspects that we are looking at. What? The probability. Then we are looking at the given time, given location, and the given intensity. Okay. So that means safe to say that is a probability, isn't it? Between 0 and 1. And this is what I have already mentioned. If you want to take the steps, mathematically, this is how that define. So susceptibility is a function of, in the case of landslide, inventory and the conditioning factor. All the conditioning factors like what we are dealing with right now, which is good, right? Hazard probability is the function of susceptibility because susceptibility essentially is estimating the location, the spatial footprint, right? And the triggering factor. This is where actually the time comes in. Okay. Now the triggering factor, it's not just the rainfall. When we do not have much time, much data, then obviously we just take as a triggering factor. For example, in the earthquake-induced landslide, when you want to estimate the earthquake hazard map, what you will do? That means you have to take the various degree of peak ground acceleration. That means if at 4 peak ground acceleration, what would be the scenario? 5, what would be the scenario? 5, 6, what would be the scenario? So, and when you change the peak ground acceleration, obviously your locations are going to change. Correct? Now you see the difference. Susceptibility is fixed because there is no time stamp there. Are you all understanding it? Okay. So that is if we take, let's say, in the earthquake-induced landslide, or if it is rainfall-induced landslide, then obviously we would like to estimate the rainfall threshold. Let's say cumulative rainfall and anticipated rainfall of 48 hours or 72 hours, if it is exceeding, let's say, 200 millimeters. Okay, these are the areas that we should do. Or if it goes 3 days of continuous rainfall, which are the areas that we should do. So now you can see understand the concept. There is a very, very definitive time factor that is being factored in. Okay. And risk, obviously, we will learn about it, but risk is obviously quantifying the values. That means hazard, vulnerability, and amount. Okay? Clear, everyone? See, although it sounds very simple, but you can see when you want to do this and perform the analysis mathematical modeling, if you do not understand actually the definition clearly, it is going to be a disaster. Okay? This I have already mentioned, isn't it? So probability means what I am referring here, the spatial probability. Temporal probability I have already explained to you. Then magnitude probability, that means what is the intensity and magnitude. But obviously not all kind of disaster you have that. But certain disaster geohazards obviously you have the magnitude and intensity, such as earthquake, such as landslide also, okay, and so on. Why do we do the modeling? You know those guys, the good-looking guys, when they walk in the ramp, they call being called as model. They're paid very handsomely, isn't it? What is modeling? Why do you need to do modeling? Modeling is a representation of something which is perfect, but the perfect doesn't exist. It's a model, right? Perfect doesn't exist. Okay? So, this is simplification of reality. And we do the modeling understand actually the complexity of the scenario that is happening. Okay? And therefore, we use different kind of mathematical models to establish the relationship between these variables, so that we understand more and more and more. That's why in the frequency ratio model we try to understand. Okay? And models are usually used for creating the simulation, forecasting or nowcasting. Forecasting means a little bit ahead. Forecasting, right? Nowcasting means right now. That means real time. Real time. As the data is coming in, it's getting fine tuned, and then you are those actually who does trading, stock markets. Forecasting doesn't work really, okay? Because there are so much of sentiment things that goes in. But let's say company, okay, very well to do company in the Nasdaq or whatever, okay? Now that this morning the company director or executive company has already resigned. How great the company is, it is to resign. So your forecasting doesn't work there. Maybe 3 days ago you have forecasted, you have told your client now that actually you are a high-fi trader. Now you have told the client, okay, put in there about $3 million. This is the stock that you should buy. Just right. So therefore, these days, these machine learning-based models, they have the ability to fine-tune the decision-making process. Okay? That means as the data comes in, at this particular time, whatever the forecasting that has happened or nowcasting that is happening, with the new data is coming in, it refine, it tune, okay, with the condition, current condition. That is why the deep learning, okay, and the CNN, the convolutional neural, RNN, the recurrent neural networks actually is very, very powerful in forecasting things in a real-time scenario. Because it learns by itself, stored in the memory, new data come in, then refine it so that it minimizes the risk, reduces the error. Okay? And with a model we can answer obviously what if scenarios. If this thing happens, what will be the scenario? That thing is going to happen, what will be the scenario? Okay? But because we are simplifying the whole process, so it's not 100% always accurate, right? It's a model. That's why we have that accuracy. But nevertheless, it is extremely difficult when you are dealing with complex earth environment to predict something. No one has ever predicted actually when is the next earthquake is going to happen. Has anyone predicted? Why? We have science, we have progress science, earthquake engineering, there are school guys, there are geophysics guys, there are geology guys, there are all these guys are there doing research. Why they cannot? No, because there are many things we don't understand. There are a lot of complexity that is happening within the algorithm. We don't. Okay, that's nature. Right? Got me? So the most important thing obviously in the hazard assessment is the database creation. And we have already spoken by length and breadth how to establish the GIS database. Okay, from different sources. So I can avoid this, but I can skip this. But make sure the data is of good quality. There are not much uncertainty in the data. Otherwise, see, input data, one data if you have the uncertainty error, that is going to propagate and cascade through your modeling process. Okay? So data, quality. Resolution, understanding the resolution scale, not just actually blindly converting the data from X to Y to Z. Okay? That understanding is extremely important. Alright? This is one simple example. So now, depending on, when you are talking about the data parameter, depending on how much of data that is available, right? For example, in Dhanbad, if you have, let's say, one ranger stations, okay, that is recording actually the amount of precipitation, blah blah blah, okay. Obviously, you don't have any much choices. Then maybe you have to take the nearest another ranger stations, which may be in what, maybe in Madhuban. Okay? But is it accurate? Because Have you noticed when you drive sometimes, when you are passing by, within 2 kilometers there might be raining somewhere, the other area is not raining. Okay? So that's not exactly, but then you do not have anything, you know. Rather than not having anything, you are just using some data that is already available. But that may not be accurate. Okay? But then we have actually the satellite-based data, the precipitation data, in a grid format, which is available for free. You can also use that as well. Kilometer, every 1 kilometers. Alright? So here this is the example that I was trying to show. Just one location is there, then it has been, interpolation has been done here. Okay? Using the idea of interpolation. Now, let's look the construction of hazard map in the case of rock fall. Yesterday I have explained to you different type of landslide. The rock fall is one of them. Okay? In the rock fall, you can't treat actually the rock fall hazard mapping as simply like the other type of landslide. Because the mechanism of rock fall is totally different. The numerical modeling has to be totally different. Okay? So that's why I mentioned many times, it's not just one model fitting for all applications. Okay? So in the case of hazard, what they do, they use the empirical model, they use different specific software designed for them. Like two-dimensional rock fall models. That means they do the analysis along the profile. But it used to be difficult to link with GIS, but I think nowadays you can also link up with GIS. There are also many other type of models that are developed, which are standalone, which can be able to perform the 3D modeling as well. Okay? Now, our aim actually is to couple both numerical model or all these kind of 3D model in GIS, so that we can make some meaningful information. So, can you see here? This is one of the examples. So, this is a rock face, slope. This is a rock face, and these are actually the potential rockfall area. This is the facade, and they identify the source of the potential source of the rockfall, and then they do the modeling how far the rock could travel in the case of the rockfall. So that's how they do the trajectory modeling. So they use like mounts, how the rock is going to bounce, how much of kinetic energy that is actually going to bring. Okay, all those analyses. I'll show you some example that I have done also, some consultancy many years. Okay. Understand? But now in order to do that, obviously, you must have good quality data. Okay? See? There is another software they use, CodeForm, which is university by, prepared by the University of Luzern in Switzerland. Okay? You see? They calculate the source, maximum runout, and so on. A lot of literature that you can find if you are interested in this kind of problem. This is another example you see here. They use in this case 1 meter LiDAR, very good quality resolution. Okay, and you can see they have different types of color, shows the degree of the thread actually this rockfall are going to poses. Okay, here is 10 meter, obviously you can see that is already pixelated. 1 meter LiDAR, this is 1 meter LiDAR, and obviously they do velocity also, they calculate the velocity of the rock. Then this is 10 meter, also they calculate velocity and all those things. And so, how to do this? What would be the potential input data that we would like to take? So far we have seen many examples, right? If I would say, or after most of you are MTech students, right, or PhD students. Now that you are, after your degree, you have joined a company. The first big project that is being assigned to you is that we have received actually a big project to estimate, to calculate the rockfall hazard assessment in the Leh-Ladakh highway. That is about 350 crore total budget. Okay. Now that you are a PhD holder, posting your ball, knowing everything about geospatial stuff, modeling stuff, you are the project manager. What would be the first solution that you would give? team will be provided to you. Okay, a team, 20 people, some of them are mathematicians, some of them will be spatial engineers, remote sensing background, GIS background. So as a project manager, what will be your solution? Yeah, when you design the project, what is the data collection? What is the best data that you have? See, the cost is already fixed. You're not going to go and tell actually your client that no, now that I would like to do this assessment, I want to file over this and that, blah, and the cost is going to 1,000 crore. This is right? In one of the slides I mentioned 5-6 days ago, always it is the cost and resources. Right? When I give assessment, especially for my MTech students, I ask this kind of question. As a consultant, this is the project. What do you do? Not ChatGPT, no computer, no laptop, no phone. You got to provide a solution. See, that's what actually is needed. It's not about what is the resolution of this particular satellite. Who cares? You can watch it. Another thing is, whatever theory that you have learned, how do you apply it in real life? Right? That is why you have to apply your mind. All the theoretical knowledge that you learn. Okay? Think. So now, the project cost is there, right? So obviously there are many types of input data first you can think of. But don't forget that the cost is not that much, okay? So obviously very unlikely that you can use an airborne based data. I said data, that means it will be of anything, okay? So now, depending on actually what is the length of the study area, then I will design best by doing the cost analysis, what will be the perfect input data, optimized data for within this cost, without compromising much about the quality of the output. Okay? That's the reason I have told you different data sources. That's the reason I have taught you why the different data sources play a very important role. Okay? We know that we can fly out the terrain, airborne LiDAR at the cost. Okay? Or if the area is small, we can also use what? Drone-based LiDAR. Or we can also use terrestrial-based LiDAR. Or mobile is with them pretty cheap. Okay? The most important aspect here will be having a very high quality digital television model. Okay? And to do that, obviously, these are the data source first I would like to start from. The second one will be other remote sensing data. LiDAR, when you are capturing at the same time, the sensor captures very high resolution of the photos, or digital photos. Can it walk 10 centimeters? Classic. Okay? So now you can think of, now that I have very high resolution photos, then I have actually the LiDAR data for clouds, which is very high density. There is also textual information. When you are collecting the data, can we actually make use of all this data to prepare maybe a combined data set, composite data set, which can help us actually to identify the potential rockfall source areas. When you say for potential rockfall source areas, I would like to know the fracture pattern. Right? So therefore the quality of your data will depend on what are you looking for. Okay? And then other variables you derive slowly. Then you define actually what is the threshold beyond which. Okay? Then you do a good field assessment. Okay? And what are the previous rockfalls that has happened? What circumstances that they have? All those information they are going to be critical and useful for your project. Okay? Are you all getting it? See, you must anticipate this kind of work when you go to the mock course. You go to prepare yourself. Okay. Now, so these are the different kind of. Okay. This is a project I did in 2004. Now it's what? 2021 years ago. So this is a project called National Data Information Management System, NADI, which we developed with the Malaysian government. Okay, this is about $150 million project. So in this, at that time, we wanted to use the GI information, geographic, this geoinformation based technology, so that the disaster management team can make use of this information for response. Only one also. Okay? This is Penang Island, which is located in the Bay of Bengal, which is a very popular island actually in Malaysia. Okay? You can see this used to be the longest bridge in Asia those days. Now there has been another bridge here which is about 27 kilometers. Okay, and this used to be a very popular, obviously very popular tourist destination. And then they used to have a lot of landslides. Malaysia being in a tropical climate, being close to the equator, so obviously we used to have about 2400 millimeter precipitation annual. On an average, so plenty of it. 2,400 mm. Okay? So what we did, we looked at all the archive information that was available for 40-50 years, approached all the agencies, because this project was under the Prime Minister's Department, so we had the liberty of getting that access. Otherwise, no agencies talk to each other like here. But now it is being harmonized, it is being now centralized. Okay, so through this project we did that. Okay? Then we collected all the information, did numerous field trips, and then we collected the landslide areas. So, okay? So there are many types of geohazard that we did, landslide was one. Okay? What you see here, this is one of the final product, demarcating the landslide hazard solutions. Okay? Because they wanted to have just 3. Okay, but obviously the paper, you have the liberty, it's a research. But when you are doing the project for a government, for a client, you go to follow what their requirements are. Okay, unless actually you can be able to convince them. This is what is better. This is what actually makes sense. Okay. Can you see the color? Very high hazard zone. And the rest obviously is, you are seeing that it is low hazard or no hazard. Okay. Can you see now after zooming in? Can you see? And this is direct over the spot 5 image. It's a very high resolution spot 5 image. Can you see the background? Okay? And on the left hand side you see those very high hazardous zones. Okay? Now, when you prepare the risk map, the risk has become very less, right? Right? Go look at the hazard and look at the risk. Why? Because risk is always associated with the socio-economic elements of risk. If it is very high hazardous, but it is in the middle of the mountain, case, there is no people, there is no assets, there is nothing that is affecting us, there is no element of risk, element at risk that is existing there. Obviously, the risk becomes less. Okay? But if the hazard is moderate, but the element of risk actually are high, the risk becomes. Okay? Are you understanding the concept? This This is the project I was talking about. This is one of the highways, major highway that connects between Singapore to the Bangkok, passing through the Peninsula Malaysia. And they wanted me actually to do this specific locations. They wanted me to do a detailed rockfall hazard assessment. So what I did actually an IR survey. Okay, then did the field survey and everything. Then we did the numerical modeling. So in the first instance, we detected potential rockfall source areas. You can see my papers. I have always made papers on this also. There's a book I have. Landslide, laser scanning in landslide assessment. From A to Z, everything is there. Okay, that's what this placement is. Okay, so now you see the different colors that it shows here, they're all being, we calculate the frequency. We calculate the frequency, we calculate the energy of the rockfall, and we calculate the momentum of the rockfall as well. Okay, these are the conditioning variables that we would like to know before we can do the rockfall trajectory. Can you see? And then we identify which are the, this is the highway, right? Which are the highway that are more vulnerable to the potential rockfall. Then once you prepare this information, then you can advise them that these are the slopes that we need to put, the mitigating measures, then you can put it to the netting or whatsoever. Okay? So this is why, see, there are different scenarios that we created. Scenario 1A, 1B, 1C, and all that. That is what the modelings are there. Right? See, and we classify the rockfall hazard map into very low, low, moderate, high, very high, depending on the, based on the classification scheme I have taught you last time. One chart. Okay? Okay, are you remembering? Now, it's not it. Okay, now, there is another type of landslide that is called debris flow. Right? Here the material is totally different. There, rockfall, the material is rock, blocked structure, rocks, fractured rock. Debris flow, basically these are soils. And the soils, which has the potential actually to, they are very viscous. Okay, you can just flow. Rainfall means just gush, miles and miles. So here the modeling method has to be different. The variables has to be different. Although they are landslides. Right? Therefore, I am telling you that for each type of geohazard, you have to have that understanding. What is the type? What makes actually this particular type of geohazard to fail or to happen? Okay? So again, this is another case study here. This is the road you can see here. We took actually the LiDAR data. We had a lot of money on this thing, so we took the LiDAR data. We calculated, you see, separate, different steps that I am showing here. We calculate the max. First, we calculated the debris flow potential source areas automatically. So we developed actually a program in ArcGIS based on certain variables and some thresholds that we created. Then, based on the local conditions, we identify the potential debris flow source areas. After that, we calculate maximum flow height, maximum flow momentum, maximum pressure, then maximum velocity. These are the 4 physical variables that we estimated before we can do the run-out distance modeling. Run-out distance means source ये रहा, कितना दूर तक actually material detach होके जा सकता है. Okay. Sometimes people will be thinking, oh, landslide maybe just small near the highway or whatever. Sometimes it can be beyond kilometers. Okay. ये जो बात in last year in Kerala, that was a debris flow. It's not that there's no landslide that has happened in the past, it has happened in the past. People are aware of it. But, nature will happen. Okay? And you see, what I have on the backdrop, I have put actually the LiDAR DM. Isn't it? The hillside. Can you all see? This is the hillside. So it's nicely shows. This is the highway also can show. So the presentation is also very important. Like when you are calculating something, producing some information, how you present to the authority, so that they see that wow, they'll be blown away. GIS allows you to do all this kind of nice presentation as well. Okay? Now I do the simulation. Run out distance model. You see this. All after taking all these variables and everything, now we did actually the run out simulation modeling. It tells the whole story that how much of material are going to be detached, what is the height, and what are the areas and how far it is going to travel, and which are the areas in the highway it is going to hit. See? Application of geoinformation. And you see, the flow height also tells you. You can quantify the volume of material. Okay? Then once we establish the framework, we wanted to do a batch processing. Let's say when there is a triggering, that is something happening. It's not only one debris flow is going to happen. You don't do actually the modeling for one. It could happen actually 3 or 4 at the same time, right? So therefore we get the batch processing, and we also did for different study areas. The next one, this is a very popular tourist hill station like our Shimla, okay? That is there called Cameron Highlands, famous for tea plantation. Very, very famous for tea plantation. I have gone there maybe 100 times to collect the data. Okay? So we tried to see that whether this little hill station has got some degree of threat coming from a potential debris flow. What we identified, some of the debris flows which about 2 kilometers far from the town also has the ability to come and hit the town. This is what actually the government and authority would like to do. Then they can see that, okay, these are the houses actually. Then they can take them creative. Okay. For the debris flow also they use the netting as well. Strong aluminium, the what you call GI galvanized, yeah. So that actually, so that it can protect the material coming in. Okay? Now, are you all getting me? Yes. First order stream, second order stream, third order stream. For third order stream also you can derive the catchment, right? In GIS. So obviously here I would like to know the small catchment. Okay. So then I'll show you if you're interested. I have understand what is spatial probability? Location, temporal probability, time, size, volume probability. Also, I have shown you now the different scenarios. How much of material, size, volume, runout probability also I have shown. Okay. So you see, there are so many types of terminologies that are being used for assessment. Okay. Now, spatial probability, how to do it? Based on historical event. Sometimes what happens? Those days, 100 years ago, GSR, the geologists will go look at this face of the hill, then they would just draw, the field that shows like very potential. Comes from the expert opinions. Also possible. They have the knowledge. Those days. Now we had, because of Madhyam period, we have a lot of data which is ability. So now we don't do that. Or maybe you can include some expert opinion. But obviously you want to quantify. Historical event, direct mapping, expert assessment, statistical analysis, empirical model, numerical model, spatial models, dynamic spatial model. I showed you some dynamic spatial model as well. Right? So different ways you can calculate the spatial probability assessment. And good thing is that all this you can be able to use the GIS. Some of them not empirical methods, some of them like numerical modeling those by using. They are not using GIS, but it doesn't matter. I can bring that. They have mentioned to the GIS and not. Okay. How do you calculate the spatial temporal assessment? This is a case of example, right? In the case of landslide, I did explain to you like rainfall threshold, like anticipated rainfall. If it goes beyond 120 mm, these are the areas are going to be having landslide or to have landslides. Okay? So rainfall threshold is the process. And parameters that what we use here: density equation, 1 day rainfall, 2 days rainfall, anticipated rainfall, or ongoing rainfall. But obviously ongoing rainfall you can't do it because you are doing the modeling first. You are forecasting first. So historically you have to do the assessment. What are the landslides or debris flows that has happened, and what are the corresponding rainfall that has happened. Not just actually during that time. Maybe sometimes what happens is that maybe there are 3 days of rainfall. Okay, imagine this. 3 days of rainfall. Soil has already been saturated now. Okay, now there is no rainfall for 2 days, but this is already saturated. Now the next batch of rainfall comes in half a day. So in this case, the triggering factor is not the half a day of rainfall. Yes. That is where your understanding has to be there when you are calculating the threshold. But in order to do that, you must have a complete inventory. That means you know exactly this particular event has caused this many number of landslides. Okay? So the spatial temporal analysis, what we do, hazard equals to the temporal, the P of PT, can you see? PL is the location and PS is the probability that you have a particular size. S is the size. Can you all see here? Time, location, size. Okay? And this probability. It can be done independently also. Right? When you spatially doing that is susceptibility. Temporal, some people do just temporal assessment. They don't do spatial. They just use the Prof and the Excel sheets and all that. Possible. Okay? This is a student that he graduated, a PhD student of mine graduated in 2012. We did actually a study area and we established, so obviously landslide is a very well-known journal, especially this domain. Okay? So what you see here, see we took, look at this graph, 15 days anticipated rainfall, 15 days anticipated rainfall, and cumulative daily rainfall amount. Then we plotted actually the landslides that has happened. And you see that we came up with actually the threshold values. Okay? Then we classified landslide unlikely, minor landslide, major landslide. Obviously, the more amount, these are the major landslide. This is how the distribution that has happened. Then you calculate the R as well, right? It's not a big deal. This is the threshold, see, and the reliability is this much. Similarly, we did it 30 days antecedent rainfall, and then we calculate the same thing. And here we took cumulative 2-day rainfall amount. This is daily, this is 2-day rainfall amount. The reliability is to 99%. Okay? So this is the relationship between the daily rainfall and the antecedent rainfall. Okay? So what we did, the entire result, we broke it down into different small regions so that we can understand more. There's some landslides depending on the different type of materials and all that also, right? So we do not want to do the batch processing for the entire area. Okay, can you see? And we had, these are the stations as well. Yeah.
What are the major differences from this system? Like we can see reliability when we are taking daily rainfall. So at that point of time, we identify the sources, but when we are accumulating those 2 days rainfall.
It is better. Better. That means the antecedent rainfall cumulative is providing much more. Actually, information to understand more about the rainfall threshold, accurately predicting the rainfall threshold. Okay? This is actually, see, there are many events that we mapped. This landslide happened in 2012 and falling in what category? 1 year hazard probability index that we calculated. Okay. And luckily, when we are calculating, then by then already 6 months has already passed, and then we have already produced those information. These are the critical areas. Already published the paper. That's right. So all this media and everyone is now running after you. Wow, you predicted very accurately. Okay. This one is landslide hazard modelling 27. Can you see here? These are the probability. Here we are not classifying. We are just saying probability. Sometimes not according to smart. Unless your data is 100% good, everything is good, then obviously you are pinpoint. Otherwise it's safe to say. It's probability. Okay. Now the next thing is magnitude frequency relationship. Magnitude, what? Frequency relationship. And we know that in magnitude high, frequency is generally low. In the case of high Richter scale, you would have very setup. Okay? So low Richter scale, you have many times. Okay? So in most of the hazard event that you can see, it's always actually inverse relationship. But except the flood and drought. Right? Because in the flood and drought, you have that bell shape. Because drought actually sometimes can run into 100 years, millennium drought. Like Australia is having drought since 1900 something. It's still in drought. One fine day, Australia will be having more water. Rainfall is declining. And you know, 70% of the country is desert. Nothing can be done. 50 degrees and above. You can actually boil the egg, not boil, omelette you can make. If you are driving, put in the bonnet. Break actually, yeah, you can see here, what is it? Yeah, forest fire not because of this, forest fire, see, again, forest fire, because Australia, the natural forest is basically 60 million years old forest, and mostly it is eucalyptus. Eucalyptus is basically has the potential of burning ability because it has a lot of fuel combustion in plant, right? उसका इसलिए तो स्मेल आता है, इसलिए तो उसको अत्तर भी उसमें निकालते हैं, right? हिंदी में क्या बोलते हैं? नीलगिरी हम लोग बोलते हैं. Why is Nil? In India also we call Nilgiri, right? Especially the eastern side. Nilgiri, there also we call Blue Mountain. In Sydney, the Blue Mountain is very common. Why it is called blue mountain? Because it is all eucalyptus. And eucalyptus, what happens is that when the sun light interacts actually with the leaves, basically a lot of blue rays are being scattered, making the entire vegetation, although it is green, looks like tropical. आपको भी पता था, इसलिए हम नीलगिरी बोलते हैं ना, right? हरा तो नहीं, वरना why is the green supposed to be green? Why you say? Okay, so those are the things. This I will explain. Disaster type and hazards are purely natural and hazards are purely man-made. I don't think extraterrestrial. I think I have shown you one of the first lecture, right? No, you are looking log of. अरे भाई extraterrestrial का asteroid impact, that is what? Natural. Then you have geodynamic process, earthquake, tsunami, volcanic, that is also natural. External geodynamic, landslides, soil erosion, hydrometeorological, flood, tropical storm, drought, ecological, pollution, crop disease. As you go downward, it becomes man-made, and then or man-induced. Remember one of the graph I showed later. And then war, that is not actually natural. War is made by us. Okay. So similarly, I put some question you can understand. We are not going to all of that. Magnitude frequency relationship holds true for many different disaster types, but as can be similar, but not for all. I already mentioned. Okay. Hydrometeorological type of disaster, lightning, hailstorm, tornado, intense rainstorm, flood cyclone, hurricane, drought. What are the occurrence possible? Okay. Sometimes they can be seasonal. That is what the temporal, right? Spatio-temporal means like when you try to calculate the magnitude frequency. Frequency is what? Frequency is the how often, right? So then you have seasonal, storm period, tornado also seasonal, and so on. Geological can be continuous. That can happen anytime. We don't. It's not seasonal, right? Does an earthquake wait for actually Diwali time? Or only Ganpati Bappa ke time earthquake comes in? No. Right or no? I'm sarcastic. No, right? Earthquake doesn't look for auspicious occasions. Correct? Similarly, you have to understand when you want to estimate the magnitude frequency relationship. I have put different types of it. Coastal erosion. It used to be occasionally, but now I think it is everything has become haywire. Okay. Hazard modeling, when the probability is essentially is between 0 and 1. 1 means that you will die. Okay? And 0 means you can swim across the Atlantic. That's what actually I have given a very simple example. 0 and 1. Okay? Alright, so I think this is about hazard. The next part we will have right now. The next part we will understand the risk. Then we are done with hazard and risk. Okay? Then the next part we will all understand about the applications. Then we will continue on our own. Okay. Now let's have a break. And then I want to show you. Can you go to the Google? What is Google? Search. See here. This is a book. If you are interested, I can. So, laser scanning application and landslide assessment, right? So, what have I done here? You can see. First, I have given ledger scanning systems, landslide studies, review. Then the detection techniques, how to detect the landslides using the cutting-edge techniques, such as here, supervised object-based detection of landslide and man-made slopes using urban ledger scanning data. Optimized rule set for automatic landslide characteristic detection, okay, automatizing the process. Integration of LiDAR and quick part data for automatic landslide detection using OBI, object-based analysis. Then every plus source identification. That's what we have mentioned. It's not the case study, right? Here, every plus source identification in tropical dense forests using airborne ledger scanning data and flow R model. So this is the flow R model that we use. This is a free model. You can also use it if you want. Then landslide susceptibility mapping, modeling. Landslide susceptibility modeling, optimizing the parameters and the effect of factor, the contributing factor. Okay, that's a separate chapter on that. Effects of the spatial resolution of different types of digital elevation model and its spatial resolution, how it is impacting actually the susceptibility mapping. This is a very good chapter. Then spatial prediction of landslide prone areas through K nearest neighbor algorithm. At that time, it's a new algorithm that actually we introduce here in this particular domain. And logistic regression model using high resolution airborne ledger scanning data. Next, spatial prediction of landslide in a stretch using Pradhan, because I have developed actually the landslide early warning system that is being used by the public works department. So I had a lot of data from Pradhan. Okay. Ensemble disagreement active learning for spatial prediction of shallow landslides. Performance evaluation and sensitivity analysis of expert-based statistical, machine learning and hybrid models for producing landslide susceptibility. Read this. This is a wonderful piece of information that you would find. Okay. Landslide vulnerability and risk modeling. Okay. Slope vulnerability and risk assessment using high resolution airborne ledger scanning data. Then landslide risk assessment using multi-hazard scenario. This also theory I have already mentioned to you, right? Using logistic regression, I have already talked to you. Okay? Then it comes to the debris flow modeling. Okay? What I have done, debris flow susceptibility assessment using LiDAR data. Then rock fall hazard assessment. Just now I showed you some examples. Here, rock fall hazard assessment and overview and application of So, second one is